Well, that was nice that he did it. I don't know. I'm probably gonna leave it on for today. Do the whole thing. Somebody wanted TriQuizzard points updated. Aha. Hey, Carl, how's it going?
Good.
Cool. You can hear me even through all the accoutrement. I will. Oh, you better. Yeah, I know it's frozen. Thank you. All right. Make sure you guys have, do you have your laptops with you? It's going to be helpful if you guys have to get into breakout rooms. We're in a group, half of the group will be not in class. Because I don't want people to feel like they can just, if they're not in class. Plus, then somebody gets to help me and let me know if staff is asking questions. You guys need more. So that morning. How was you guys' weekend? Yeah, that's not part of the miss certain classes and things to do. You don't schedule it this all. Schedule it this one. So you get everybody in. Oh, 2 minutes. 2 minute warning. Yeah, it's a pretty light in-person class today. You guys online can't tell if you're supposed to be in class or not. If you go into LoudCloud on the roster, it will tell you if you are a Tuesday or a Thursday student. Obviously, if you're TOS, just make sure that you're presentable with your camera on. Morning. You can sit wherever you like. Just make sure that there's only 2 people per pod. So, um, sorry, what was your question again? So there are specific extensions. It is in LabParty. That's how I know where it is. If you go to the roster, it should list you as a Tuesday or a Thursday student. You are, in fact, a Tuesday student, though. So good job. All right, guys, it's 9:45. We are going to get started. Can everybody at home hear me okay? Is this a good volume? All right. All right, let's get started. Lord, thank you for bringing us together this morning. Thank you for the weekend and hopefully the rest that we got. Help us to stay focused this week, to get used to the new schedule of when we're supposed to be in class and when we're supposed to be online. And just help us to stay focused and concentrate on what we need to do. In your name we pray. Amen. Okay, so what are we doing today, right? What are we doing today? Sweet, thanks. All right, Ron, if you would please be the person to man chat for me today, that would be terrific. If you guys have questions, you can put them in chat. Now that I have a captive audience in the room with me, I can have them do things like read the chat and make sure I don't miss people's questions. So it's going to cycle through everybody, right? So thank you in advance. Appreciate that. All right, so what are we doing today, right? I'm going to recap last class, and then that's not correct. We're not going to talk about solenoids today. I hope these are the right slides. Boy, howdy. Well, we're going to go with it. We're going to see what happens. So, like, upload it this time. Anyway, so we're going to recap last class, and then we're going to continue on with what we had been doing, right? So we're going to do more example problems. Okay, that's basically it. So what did we talk about last week? And so KVL motor KVL. Kirchhoff's law seems to be what is the most, I guess, challenging to for us to grasp right now, right? So what about them? Well, KVL is for loops, right? KVL is for loops. Anytime you have a closed loop, you can use KVL. KCL is for nodes. Anytime there's a node, you can use KCL. What is a node? A node is a junction where 3 or more wires are entering or exiting, right? You can do it for 2, but it's not interesting, right? It's going to tell you that whatever came in is whatever is going out. Think of it like a Think of it like a pipe system, right? And we'll get more into pipe systems in Thursday's class, right? So think of it like a pipe system, right? If you're flowing water through a system of pipes, if I have one hose, right, and I, drew a control volume around like half of it, the amount of water coming in is the same as the amount of water leaving, right? This is the same as current, right? It's the same as current coming in as the current leaving. If I had a hose that was really sweet and like forked itself into 3 different ends, right, then you would have to split that water flow, right? That is what KCL is telling you. It's telling you how much of your current is splitting. The amount of current that splits depends on what elements are connected to it, right? So if your special tri-outlet hose, if one of them was really narrow, right, that would be like a high resistance. So that would change your current in a certain way, right? If one of them emptied out into a tank, that's like a capacitance, right? So based on what they're connected to is how we figure out how much current we have, right? So if you have a capacitance, it's going to act differently than a resistance. It's going to act differently than an inductor. Okay, for motors, right, all we're doing is we're taking what we know, right? So the last problem we did in class was the motor, right? A simple RL circuit connected to a motor, right? And I say it's a simple RL circuit because it only had one resistor and one inductor, right? So we just do a KVL, right? We've done that problem in class before a couple of times. What we're looking at is how do those things couple, right? And they couple through the magnetic field produced by the inductor, right? Which is driven by what? Well, driven by the inductor, right? So there's those things. We came up with a bunch of expressions for motors, but really if you just treat it like a circuit side and a mechanical side, right? And you do each of those in a bubble, you should be able to work your way through them, right? And we probably feel a little bit more comfortable with mechanical systems just because I understand there were issues with circuits when you guys took it, and I get it, right? But KVL, KCL, Ohm's law, and the inductance and capacitor ODEs are really the only things that we need to solve any circuits question, right? All right, EMF, the electromotive force. Well, you see, if you have a wire moving in a magnetic field, it wants to produce a voltage, right? And that's where that back EMF comes from. We can treat back EMF like a force, right? We saw that on the previous problem, the last problem from last class, right? The motor. Back EMF gets treated like a source because you're producing a voltage. Now with the motor, you have this interesting coupling, right? Because the more current you give it, the faster it's going to go. Right? And the faster it goes, the more voltage it's going to, more back EMF it's going to produce, right? And so if you look at those equations, back EMF actually gets treated as a sink, right? Not as a source. We are actually fighting against that. You can think about that almost like friction mechanical system, right? It's eating some of your voltage. It's eating something off of your system, right? And you need to overcome that, otherwise you'll start spinning in the opposite direction. Right. Okay. You guys have any other questions? Okay. Oh man, are we gonna see another motor today? Right? Let's see. We'll see a solenoid today, which is kind of the same thing, except instead of rotating, right? So really, I'm going to simplify it way down. Like right now, really the thing is that the difference between a solenoid and a motor is that one spins and the other one translates, right? One rotates, one translates. They obviously are used for different things, but how do we change a force into a torque, right? That's the whole question 9 on the homework, right? You have this lever, but you have a force applied. What's the torque, right? Well, the torque is the force times the perpendicular distance away from the axis of rotation, right? If we know that for a motor, right, if we are applying some electromotive force to our motor, and we know how far away it is from the edge of our, or from the axis of rotation, that's how we transformed that into a torque, right? That's how we got that motor torque equation. All right. You guys have any other questions right now? Burning questions? Doing my best to stay loud, guys. I'm doing my best. Give me 1 second. See if I can alter the gain on this a little bit. See if that helps at all. I've fiddled with my game, so doing my best. Okay, here are the things that are due. All right, let's do the things that are due. You guys all did your ethics paper, hopefully. You got homework 2 due this Sunday, exam 1 a week from Thursday, and homework 3 due a week from Sunday. Everything up through and including next week's class on Tuesday is exam eligible, right? So on Thursday this week, next class, we are going to jump into fluidic systems, and then we'll hit thermal systems next week on Tuesday. Right, that's the plan. Okay. So let's just hop right in. This one was assigned to Jaleese. Please, here, I will stop sharing. You can share your screen if you can. If you'd rather show us what you got, that's fine too.
I wasn't able to do too much, probably just the ins and outs along with the mathematical truths.
That's fine. Let's show us, just go with what you got, and then we'll work through it together as a class. So,
Okay. Right, where did I put the page? Sorry, slight technical difficulties as I actually find the page where these Apple problems were on.
okay. So we talk while you're looking for it. What should the inputs and the outputs be? Why don't we talk about that?
Well, the input should be the ENT that comes from the main battery, for one, and the output should be the E0.
All right, so if we're looking at this, where would E0 be? Where would the output voltage be? All right. Right, I guess it's right there. That's a stupid question. I'm looking at the wrong one in my notes. I apologize.
It's fine.
All right, so normally you would be right? But in class, what have we been using as our inputs and our outputs exclusively? Right, and this is my fault because I grabbed this from a book that's not our textbook, right? What did we say our dynamic variables are exclusively going to be in our dynamic systems or circuits? So I think I heard somebody say E naught. That's only for op amps, right? It is, in this case, it is E naught, but that's because E out represents the voltage drop across the capacitor. Right, so there's always, for regular circuits problems, we're going to deal with E in or I in as our, anything that has an in on it, it's going to be our input. And we're going to have the current through the inductor and the voltage drop across the capacitor. All right, those are the two dynamic variables we're going to deal with. So E out is technically right because that is the voltage drop across the capacitor, but we're going to want one equation for each I sub L and E sub C, right? Because we have two energy storage units. And because we have two energy storage elements, we need two first order differential equations to describe. This is a second order system, right? So
I was a bit confused on what to do with the switching amp, but I do know that for the mathematical truths, there was L becomes Li, R becomes Ri, and C becomes Ce dot C. I know there's a KCL, and there may be a KVL, and that was as far as I got.
Mm-hmm. Sure. All right, cool. Cool. So let's, thanks, Jalise. Let's talk about it. I'll pull up the picture. Right? All right. So here's our system, right? Let's forget that this is a thing here, right? We'll just call it E sub C, right? But it's not going to help when I pull up my diagram here. All right. So how do we deal with the switch? Right? How do we deal with the switch? Yeah. Yep. You're basically going to draw this circuit with the switch in position 1. And you're also going to analyze it with the switch in position 2. Right? So you have to come up with two models, right? Because these are two very different, well, they're not very different, but they're two different. Right? You have two different circuits. Yeah. They are going to have the same inputs and outputs. All right, so let's. All right, so we'll have some current coming through here, right? I'm going to call it I sub L. Right. So when we're in position 1, the voltage comes up, right? We have some current coming up, traveling through here. Right. The reason I'm calling it I sub L is because it goes through here as I sub L. Then what happens? We hit a node. So we're going to split. I'm going to call this I sub A coming out. You could also call it I sub R if you want, because it goes across the resistor. And how much do we have coming down here? I sub C. Okay. We come down to the case where position 2 is closed. Now we've taken this voltage input out of the loop here, right? So basically, if you flip the switch, this is going to continue to run for a certain amount of time, right, until the capacitor discharges and the inductor doesn't have any more energy, right? And so you would oscillate this where you charge it for a little bit, turn it off, let it discharge, charge it, let it discharge. Kind of like the video we watched about inductors where if you turned it off, the inductor would then keep the lamp on for a little bit, right? Kind of like that. So what do we have current-wise in here? Well, still going to have IL, IA, and IC, right? We're still going to have that. But we can also talk about this in terms of loops, right? In terms of loops. And so I've got voltage loops that we can talk about like that, right? There's 3 in each case. Typically, when we do a voltage loop, it's beneficial for us to pick the ones that have both of our elements together, right? So if you can write 2 differential equations in terms of each other, right, where you have E dot is in terms of IL and I dot L in terms of E, right, E sub C. That's where you kind of want to be. You want to have 2 coupled ordinary differential equations. Reason for that is when we get to state space, it's going to be really easy to just plug that in to a state space representation. All right, everybody's good so far with this. You doing okay? Yes. Okay. So we do now our inputs and our outputs, right? So our inputs and our outputs. So I'm going to write my inputs and my outputs based on my switch positions, right? So I've got switch 1. And for switch 1, I've got an input of En of T. Right? This is my input. And my outputs are going to be I sub L and E sub C. These are my outputs. Then for switch 2, what do we have? Well, what's my input for switch in position 2? It's tricky, right? We don't have an in. It could be E sub C. It could be I sub L. It's not really anything, right? There's something that's already in the system. If there's potential that's already in the system from that will drain it, right? So the input's nebulous. It could be E sub C. It's likely that because we had E sub C and I sub L, our output will also be these 2 things. Right? Yeah, Dan.
Would there be a scenario where you have E dot use it out? That'd be helpful.
Well, E not C?
E dot.
E dot C. I mean, you will probably have E dot as the output because it's a differential equation. Right, we're just keeping track of what dynamic variables we're expecting to be the output, right? So,
That's very well.
yeah.
When you say dynamic variable, do you have like the vector possible variables? Do you have like you include those dynamic variables?
So it's anything that changes with time, right? Anything that's time dependent. So yes. Yes.
Oh, yeah. Well, yeah. Variable. Say you input dynamic variable. You say you see just you see.
You mean all variants of ECC. Right? So it's if you're thinking of it as state space, right? It's anything that could be in your state variable vector, right? Anything that's in your X vector. Okay. All right. Cool. So what about our truths? Well, our truths aren't gonna really change that much, right? We've got this guy, right, for Ohm's law, and we've got, our inductor truth is L I dot L, and I've got my current truth, which I wrote as I sub C equals C E dot C. We're going to have KCL at our node, which is going to be the same, right? This is going to tell us that I sub L is equal to IR plus IC. And that's going to be helpful right off the bat, because that's going to allow us to get our current through the resistor in terms of our dynamic variable, right? That's going to allow us to plug in some things and figure out what is I dot L and what is E sub C, right? We also have our KVL, but let's go back and look, right? So these are all the same regardless of whether we're using switch 1 or switch 2, right? Those are all going to be the same. We're using the same setup for all of those. What is going to change are the KVLs. So when we have the switch in position 1, right, let's go back and look. What's my KVL? Well, which one of these should we, what do you guys think? Should we use left-hand side or right-hand side for switch in position 1? Right-hand side, because why? Okay. So for this particular problem, it doesn't really matter, right? Because you're coupled through that current, right? We already know that the current through the resistor is a function of the inductor and the capacitor. So it doesn't really matter, right? Because you're just looking for a way to get everything in terms of I dot. So you want one equation for I dot sub L and one equation for E dot sub C, right? That's what you want. Why? Because we need a first order differential equation describing our energy storage, right? That's what we're looking for. Because of that, I would probably choose the left-hand side. Now, again, it doesn't really matter whether you choose left-hand side or right-hand side here, because so for circuits, and this is the thing that frustrates people, there's multiple ways for you to do this and still get an answer that is reasonable, right? So what you should be looking for is that you have at least one, well, not at least one, that you have one differential equation in terms of each of your outputs, right? So in this case, we want an I dot L equation and we want an E dot C equation, right? That's what we want. So what is our KVL here for left-hand side? Well, that's, because remember too, we need it in terms of the input, right? Without KVL from the left-hand side here, also, we don't really have a way of bringing our input in, right? So we don't have the cause to the effect. We just have the effect. Will E in be in all of our equations? No. But these are coupled through each other, right? Through that current line. Right? Through that node, these things are all coupled together, right? And we'll be able to track E in all the way through the circuit. All right, so we've got E in minus EL minus EC, right? So we've got KVL, left-hand side, En minus El minus EC is equal to 0. And for the switch, number 2, we've got our KVL of the left-hand side, and that's going to be this. They're both sinks. There's no source in them. And we'll just, that left-hand side just cuts out our E. So we can think of this as negative E sub L is equal to EC. Right. I'm gonna do that. All right. Cool. We good so far? Yeah? Maybe? Maybe not? People at home? Viewers at home? This is like the world's most exciting game show, right? Because you guys get to participate. Something like that. I'll keep telling myself that. All right, so let's start our reduction then. All right, so why don't we start with our KCL? We'll do switch one first, just because. So for switch one, what do we have? Well, we had I sub L is equal to I sub C plus I sub R, right? And that's all well and good, but I want I sub R in terms of look like that, right? All right, well, let's plug some things in. So I can get I sub R is equal to L, or sorry, is equal to IL minus C E dot C. And as actually, I did forget a truth, right? Danny was right, we do need that right-hand side, right? Because we need to get what the voltage drop is across the capacitor, or I'm sorry, across the resistor. But we know what it is. All right, let's go back and look at our diagram. What is the voltage drop? Do I need to do an analysis to figure out what the voltage drop is across the resistor? What is it? It's in parallel, right? It is in parallel with the capacitor. So they have the same voltage drop, right? They have the same potential across. They're both connected to ground from the same point at the top. So their voltage drop will be equal. So we don't need to do a KVL here, right? You could, if you did KVL here, what would you get? You would get E sub C is equal to E sub R, right? That's what you would get. All right. So let's look at this, right? So I'm going to plug in for I sub R, right? Because I know that I can rearrange this guy to look like this, right? And rearrange that. And then I'll end up before this. Then I'm going to plug in E sub C for this, right? Right. And now, hey, if I rearrange it, I've got a first order differential equation for E dot C, right? Now I can use my left-hand side KVL and plug it back in. Right? We'll call this 1. I'm going to try to do this on one more slide, but I have a feeling I'm going to have to grab another. All right. Is everybody okay with this so far? Everybody cool? What's up, man? Yes. So the reason, okay, so again, right, if you wanted to, you can prove it using the KVL to the right-hand side, which shows us that E sub C minus E sub R is equal to 0, right? That's what it would show us. And so E sub C is equal to E sub R. And remember, You're gonna want to put a minus on that, but you're going across it in the direction of the loop. You're going across that capacitor in the wrong direction, the wrong direction, right? The opposite direction, right? So we got to treat that as actually a source for that loop. Right? That's where that comes from. But typically, when we look at that, right, you can make, so that's the math behind it, but you could always say that two things in parallel will have the same voltage drop, right? Two parallel paths always have the same voltage drops. Okay. So let's put a square around this guy, or some sort of shape that was supposed to be a rectangle. So let's grab our KVL, right? KVL said En was equal to E sub L plus E sub C, right? I just did a little algebra and moved the input to one side and the output to the other. Right? I mean, technically, right? Technically, let's go back here. Let's have Dr. D do this the right way. And by right way, the way that I keep telling you guys to do it. And rewrite it as an input-output equation. Right? Those are all outputs in that equation. There's no input in that equation. So I'm going to write it like this. All right, so if we do this, right, well, E sub N stays E sub N, E sub L is L, I dot L. That's done. That's it. That's the equation. But no buts. It's got I sub L, it's got E sub C, and it's got En. Those are all the dynamic variables that I have in my system. That's it.
What is this?
This is the KVL on the left-hand side. That's our second equation. It is first order ordinary differential equation based off of I sub L. Should you want to, you could take this equation that's in red and solve it for E sub C and plug it in, right, and do those things. I would recommend not doing that. Just leave it as two equations. Just leave it as two equations. Okay. All right, all right. Guys have any other questions on switch one? Because we can hop over to switch two. If you guys thought, well, switch one and switch two are basically the same, you just need to eliminate E sub N, and pretty much dead on. That's exactly what we're going to do, right? Because that node didn't change, right? The node didn't change. The amount of voltage drop across our resistor and our capacitor are still the same, right? The only thing that changed is we took E sub N out, right? So we should get the same exact setup as last time, just without E sub N, right? That's what we should get. So let's run through it quickly, right, for switch two. Switch two. Well, the truths are the same, right? So we found out that I sub R was equal to I sub L minus IC, right? We plugged in for this, right? We'll plug in again, right? We'll rearrange this. We'll end up with CE dot C minus 1 over r e sub c minus I sub L is equal to 0. Right? Still the same. Nothing changed at that note. Nothing changed. What did change? The KVL for the left-hand side. We said that this is now this, right? That's what we, minus E sub C minus E sub L is equal to 0. I'll just rearrange it. Okay? And in fact, let's not rearrange it. Let's leave it in its raw form. Negative E sub C minus E sub L is equal to 0. I don't need to change E sub C. That is one of my dynamic variables, so I'm good to go. All right, so I can change this to negative E sub C minus L I dot L is equal to 0. Right, and if you really wanted to, right, you could multiply the whole thing by negative 1. And we can make it L I dot L plus E sub C equal to 0, which is exactly the same as the last equation that we came up with, just with E sub n is equal to 0. You guys have any questions? Good. Some of these look a little bit more complicated than they actually end up being, right? Some of them are exactly as complicated as they look, right? And electrical systems get very fast, right? They get very fast. So what do? You break them into smaller pieces that you understand and do the piece that you understand, right? You know how to do KCL at a node, right? Do KCL at a node. What do you need? What do you need it to look like, right? You guys will see, especially when we get past the first exam, when we get into Laplace transforms, you guys are going to think that I'm cheating, right? You guys are going to think that I'm just making it look like the response that I want it to. And we'll talk about that, but you're not wrong, right? What's the point of taking all these classes if you don't use the knowledge that you already have to your advantage? Right? What's the point? Okay. Any questions? We've got more. We've got a lot more that we're going to do here. Okay. Next choice, soul. Ooh, this one looks fun. That one looks fun. Who's that one for? Vet. This one was for you. Hold on. There's also another reason why you guys want to be kind of on Zoom too during class, in case you're in class and you have to show your work and stuff. Because right now it's not. It's frowned upon for me to walk around with a camera. Just, okay. So what we got going on here? What is this? What is this? What does this look like? Does look like a solenoid. It is a solenoid. But this is different than the solenoid we did before. Why? What is different about it? Yeah. Well, so we're gonna have to model the circuit, sure. What looks different about that circuit compared to other circuits that we've done? Look back at the last RL circuit in your notes. What's different between this one that's on the screen and the last one that's in your notes? Meaning the motor from Thursday's class. There's something written in there that is not written on the other one.
Friction?
No, I mean, it has viscous friction, for sure. But I'm talking about the
What's lambda?
magnetic flux. Our current is a function of lambda, right? That is the difference. And why does that make a difference? It makes a difference because this is now a nonlinear system. And this is a function of lambda, not a function of time itself. Although lambda is a function of time. But now you've got something that's both a function of lambda and of time. Those are going to interact in some way that is non-linear. And so this one is, what do we do? Right? So what do we do? Well, we're still going to run through this. We're still going to run through this as we normally would. Sorry, guys, I am lost in my notes. So what happens when I don't put things in the order of my notes? All right, so I've stalled for long enough. Yvette, do you have anything with this problem or no? If no, that's fine. I would have liked for you to try, but you know, sometimes it doesn't work. No, I don't want anything ever collected in one equation right now. Just because I don't doubt that you guys could do it, right? But the problem is that you're going to run into needing to take derivatives and integrals of variables that I haven't given you bounds for. And it's going to wreak havoc on what your equations look like. If you leave them as is, when we get to Laplace transforms, they'll tidy themselves up, and the algebra is a lot easier. And the algebra becomes a lot easier. Give me one second. Let me make sure I'm looking at the right thing. These are, in fact, yeah, okay. So Dr. D's notes are jacked up right now. That's the nonlinear. Yeah, I apologize. This one is not nonlinear. Bum, bum, bum. All right. So this is a function of our flux, though, right? This is a function of our flux. So how do we deal with this if it is a function, in fact, a function of flux, instead of a function of whatever it is you were looking at prior? Right? We can still draw a circuit diagram. What should our circuit diagram look like? And it's basically just right there already. That's it. Right, so let's draw our circuit. And so we've got some source, the resistor. Do we have a resistor and then our inductor, or an inductor? Resistor, then our inductor, right? Here's my resistor, my inductor. I sub L in this direction, here's En plus minus. Great. We need an FPD. What's our FPD look like? Of my electromagnetic force here, right? I'm going to have, that's an F. Try that again. Then F sub K and F sub B, right? How do I know that? Well, clearly the return stream is there. We're told that we have viscous friction though, right? So, you know, that's our key word to have some damping there. And let's not forget X is positive this way, right? So this implies that we're moving to the right. And so we're going to be positive to the right. Those are our two systems, right? And so this implies that our kinetic diagram would be something like that, right? Don't draw inertial terms on FPDs, right? They're not forces. It's what are some of our forces equal to. They're not forces, though. So don't draw them. Do not include them on free body diagrams. You get confused. Also, some of the forces you guys should never, ever, 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 ever write some of the forces equal 0 on anything in this class. Ever. This is not a statics class, right? The inertial terms are equal to something. Okay? These things are moving. Please don't ever, ever, ever write some of the forces or some of the torques equal to 0. Because it's not true. You'll get dinged really hard. All right. So let's talk about this, right? What's my input? What's my output? Let's talk about overall, for this system as a whole. What is the input?
En.
En. What's my output? System as a whole. It's X, exactly. Right, so we've got En and X. Those are my global inputs and outputs, right? What if I'm just looking at the circuit? What's my input? It's still En. What's the output of the circuit?
I sub L.
What's the input to the mechanical side? FEM, which is in fact a function of I sub L, right? We'll talk about that again in a minute. So yeah, so my global system-wide is En to X, right? But I can break each chunk into pieces and write an equation for each side. So should we start with the circuit or should we start with the mechanical system? What do you guys want? Take your poison.
Circuit.
All right. Circuit it is. Circuit. Okay. So we'll start with the circuit. Mathematical truths for the circuit. What do we got? Somebody hit me with one. The RL circuit. So what do I have? All right, so We got a KVL, sure. What about element equations? What do we got? There's really low hanging fruit here, right? How do I describe a resistor? How do I describe an inductor? Right? Yep. Ohm's law, right? But we also know right off the bat that it's equal to that because you only have the one current. What about my inductor? What's my inductor differential equation? Thought I heard it. Somebody. Yep. Look at that. But it told us that I was a function of the flux, right? And that's true, it is. But we're not going to do anything with that per se right now. Why? Yes, because we know that the flux affects what? Well, the flux, what this is just saying, and remember what flux was, right? When you wrote this equation, no, sorry. Lambda is equal to L IL, right? This was from about a week ago when we talked about magnetism, right? I guess this was Thursday's class. Where we talked about, no, I'm sorry. This was from last week on Tuesday when we went over the elemental equation, right? We said magnetic flux is equal to lambda times I sub L, right? So if you take the time derivative of that, right, you can describe that as E sub L, right? So really, it's just a change of dynamic variable, right? Instead of writing things in terms of E sub L, we can write them in terms of lambda. Right? We could do that if we want. It's just a change of dynamic variable. It's like when we change velocity, or we change from working with position to velocity, right? And we get, instead of x double dot, we get v dot. It's the same concept. Except in this case, you'd end up with an integral, right? So E sub L. But if you wanted to get this in terms of just lambda, right? Another way to write lambda is the integral of E sub L, right? dt over some bound. If I took the derivative to get there, I could take the integral to get back. So we could write this in that way. We're not going to. We're just going to do this straight away. Okay. All right. So now what? That seems all well and good. Right. Based on our armature circuit, and we've got everything we need there. So we're going to pause on that. We're going to pause on our truths, right? We'll do the mechanical truths in a minute. So let's do our reduction. Let's do our reduction. For the circuit. That's for the circuit. Danny jumped it, right? When he talked about it earlier, it is EN is equal to ER. That's EL, right, which we can rewrite as what? And we can rewrite this as EN is equal to R I sub L plus L I dot L. If we really wanted to get this in terms of lambda, we could, right, with a little bit of, yeah, Sean. It's an interesting talking point. Like, if you need it in terms of something specific, you'll know. I'll let you know in the problem statement, right? If you're reading problem statements. But we're not going to write things in terms of lambda. There are certain applications, I suppose, where you might want to know what the magnetic flux is, right? But for this particular, for an armature circuit, you're likely going to be controlling the current, right? Not the, and by extension, the flux, right? Yeah. And mhm. So there it is. That's the RL circuit equation. Right? That's done. Let's talk about the mechanical system now, right? So what are my mechanical system truths? Somebody give me some mechanical system truths. Yeah. There's one. So that's the big daddy, right? That's where all of our equations come from. What's something else? What's another one that we would have here? The x dot, right? F sub b. We got one more. Perfect. Right, there we are. That's everything that we need to do this, right? Because we can sum our forces, right? Well, I guess technically, if we really wanted to, right? Can we write that FEM is B B times, no, I'm blanking on that. Oh man. Why am I blanking on this? It's B times L. Right? B times L times the velocity times the current. Right? Because you produce a, that's not the velocity. This is BLI. This is B times L times L. Right? Because what is a current carrying wire will induce a field on its own, right? If you have a current carrying wire in a field, then you have a force on it, right? Because it's already in the field. So you get B times L times I. Is that correct? Check your notes, because for some reason Dr. D has a case of Monday morning on Tuesday. So, thank you. I apologize. It's been a strange day. All right. So in this case, that's B times L times I sub L, right? Because that is the thing. Yeah, Sean. Because that is the rotational velocity. So if you're looking at the torque, right? The torque, right. So is that for the motor torque, or is that on the back end method? Yeah. No one sec. We would double check. B times electromotive force is, or FEM, not electromotive force, but the force electromagnetic is B times L times I. The torque is B times L times I times R to make it a torque. The electromotive force is going to be the one that's a function of, so E sub B, that's the back EMF, that's going to be a function of the velocity. Because if you have a wire in the field, right, it wants to induce a voltage across it, right? If you have a wire moving in it, that's proportional to the velocity that the wire is moving in your moment. So we don't have motor constant, right? Of that. So let's look at our mechanical system. If I sum my forces, I've got FEM minus FB minus FK is equal to MX double dot. right? So that's going to be B times L times I sub L minus B, different B, x dot minus K x is equal to M x double dot, and so M x double dot plus B x dot plus K x is equal to B times the length of the wire. Now, capital B, remember, is my field strength for my electromagnetic field density. L is the length of wire, and I sub L is my current, right? And if you wanted, you could combine these two equations, right? But I would highly suggest that you don't, right? Just leave it.
Do you want us to remember the BL, what the FEM equals for like the test and substitute the BLIL for FEM?
I mean, yeah. Yeah.
Okay.
Yes. Yeah. The script L there is the length of the total length of wire that you have, right? Okay. So there's that. Is there any questions on this one, right? So again, them telling us that that's a function of lambda is just them letting us know that if we really wanted to, and I'm pretty sure that the problem statement from the book that I grabbed this from wanted you to make it in terms of lambda. I don't see the benefit in doing that correctly. There's no real applications that outside of electrical engineering where you're going to want to use magnetic flux as an actual input or output. Yeah, Sean. Because that's the only current, right, that's going through that circuit. So I sub L has to be the current, right? Because another way of thinking about this is what, right? The way that we manipulate magnetic fields in circuits is through the inductor, right? Because think of how it's constructed. It's a bunch of coils of wire that we typically wrap around some sort of metal core, right? That's an electromagnet, right? That's basically an electromagnetic. An electromagnet and an inductor are basically the same construction, right? And because of that, that's why we end up with, that's how we're going to couple a lot of our electromechanical systems, right? If we're using magnetism, it's going to come from that I sub L, right? That current through the inductor is what is driving our magnetic field. The more current I put through, the larger the magnetic field should be, right? And think about like a motor, right? How would you operate a motor, right? You typically set it at a voltage, right? And you change the current that you're giving it, right? The more current you give it, the faster it's going, right? Because you're basically inducing a larger field, right? Which gives you a larger force to push. Right? That's what we're doing. Yeah. Any other questions? Can I put, all right, put it up to the group. Is that something that everybody wants? Does everybody want B times L times I on the master sheet? Is it on this? Yeah. I've been told it's already on the master.
Oh, where is it? I'm looking for it.
Under electromechanical systems. It says, yeah, so Danny says that it says IL cross B, but if they're perpendicular, then it's just the scalar, which would be IL times.
Oh,
Mhm. All right. Let's talk a little bit about solenoids then in more detail today. Talk about them a little bit. We've done a lot of solenoid problems, but we will talk about them in a little bit more detail, right? And we'll do, so what is a solenoid? What is it? What is it? What do you use it for? Yeah, again. So, for those of you who can't, who are not in the classroom, Danny has said that you use it to change a voltage into a positional movement, typically for fuel valves and things like that. And that is true, right? We use a lot of solenoid valves. It's a device that converts electrical energy into mechanical energy, right? It's an electromechanical system, right? We just did a problem. We had an electrical circuit that providing some input to that circuit gave us some mechanical output, right? So what is a solenoid made of? And when it's simplest, it's a coil of wire that's around some iron core, right? Similar to a motor, right? You've got a bunch of coils of wire around an iron core for a motor, and that's how we get a motor to work, right? So how does this work? Electricity and magnetism. I know, it's so exciting because it has an exclamation point, right? So we're all excited about it. It's our favorite. Right, so we use the same principles as a DC motor, right? In this case, we induce a field and it creates a force, right? And it's in line with our iron core, and it will slide our iron core left to right, right? We typically put a return spring on it so that when we turn off our input, it slides it back, right? So how's it different than a motor? How is it different than a motor? Yeah. So a motor typically is rotational. Well, not typically. A motor is rotational, right? And solenoid is going to be translational, right? Translates. It doesn't rotate, right? So what are some typical applications? We talked a little bit about this. So taking valves off the table, what's something else to use a solenoid for? Yeah, linear actuator, sure. What's something else? How could you implement a solenoid in your daily life? You want sure. You could have a door opener or a locking mechanism. Hotel doors are typically solenoid locks, right? Think about what you do. You put your card in. It doesn't read it the first time or the second, but by the third time, you're either really frustrated or it's finally done the thing, right? So it gets some signal from your barcode, right? Some signal from that magnetic strip that starts your circuit, right? It opens the door. Once it discharges, the lock shuts again, right? The spring engages and shuts off. There's a cool is relative. There's an interesting video on YouTube of somebody who has created their own door opener using a rotary to linear actuator in the style of a solenoid, which is pretty neat. My wife would kill me if I saw it because it does not look polished at all. It basically looks like a plastic box with a bunch of garbage hanging off of it. But I mean, you know, still a cool idea, right? So it's something you could do with minimal hardware, right? You would need basically a locking mechanism and a rotary to linear actuator, or you just buy a solenoid and do that too, right? That would work. We talked about robotic actuators, linear actuators, right? The thing about robotic actuators is we want them to be small, right? Typically, I mean, not always. We do have some large robotics, right? But for people who are trying to create robotic hands that are anthropomorphic, we want small, right? You trying to make this prosthetic hand with a grip assist, you want a small actuator, right? And solenoids can give you those small actuating footprints, right? They can provide significant amounts of force over a small space. And we talked about valves opening and closing. That's probably the most common application for a solenoid, right? Is valve systems. There's a picture, right? We've seen this picture quite a bit, right? So what happens? We apply some electrical input, we energize our voltage source, and we establish our magnetic field. The EM force attracts the armature, right? So this electromagnetic field, and so look, here's where it starts, right? We apply some electrical input. This has a coil of wires. This right here is the cross section of a coil, many coils of wires, right? Notice there's a little air gap here, right? Why is there an air gap? Because as I energize this, this is going to want to push this way, right? So it needs somewhere to go. So in its final position, right, it'll look something like that. This will get pushed out, right? Notice this is a drain. So what happens? This gets pushed out of the way, right? And allows fluid to flow from the supply. So this will then go down here. Once this closes, there's an excess drain that will allow fluid to flow out if it's trapped inside. Right, these gaps are really small, right? They're obviously not press fit, right? Because then it would move, but they're very small, so you get minimal leakage between the walls and the valve, right? Because otherwise the valve's useless if it's just on. Here we go. Dante, that'd be a great question for Dr. K. There are solenoids in MRIs, slightly different application. And I'm not the best one to talk to about imaging, although Dr. K is the imaging all-star. So, you know, feel free to give him a shout if that's something you're interested in. Right, so this is the same words with a different thing. Right? So if we simplify our diagram, our schematic, we can talk about the plunger with a coil of wires around it and the actuator, right? So this is where our lump model comes from, right? We're taking the entirety of the valve, we're making that our mass, right? We're saying that the armature is the coil of wire, right? We're consolidating the inertia from that plunger into our mass, right? We separate them out. And that's how we come up with this, right? So what time is it? All right, so how do we want to do this? All right, I'm going to throw you in your breakout groups, right? So you guys can work together. All right, I want you guys to spend, I'll give you guys 45 minutes. Work on this problem with the people in your groups. So start up your, yeah, it'll be your same teams. You gotta hit your breakout room. So I don't want you guys to switch seats. I understand that some of you are in class together. That would probably be beneficial. You know what? We've been doing a lot of group work lately, actually. Work on them solo. I'll give you guys 45 minutes. Work on this problem solo. I'll leave it up here on the board. Yep, this way. Let's work on this. It'll take 45 minutes and we'll go from there. you two at home, you can follow along and do it. If you guys have questions, let me know. I'll come over and answer them. All right. But try to get started. What's up? Oh, there is. There is a difference. This is different. That's now a function of x. So that'll be fun. You do it the way that you would normally do it, and then we'll talk about it when you guys are. But try to figure out how you handle that being not just a function of time, but also a function of position. code, if, let me give you a hint, right? If L of X, L is now a function of X, what does that mean? It means that L isn't constant. You've been running all these as L being constant, right? So, if L is not constant, how does that affect the overall equation? And remember that lambda is equal to L by L, and the piece of L is equal to lambda dot. So if you take the derivative of L times IL, but L is not constant anymore, how does that change your derivative? That's my hint. Let's show of hands. How many people have diagrams? You guys at home, you have diagrams. Do we have diagrams? You can respond with a reaction or words or in the chat. We have our diagrams. Personally, I like the thumbs up reaction. I also like the party one that has the confetti. That's a good one too. Let's talk about our diagrams here. Let's talk about it. How do we do it? How do we do our diagrams? Right. Well, the second one basically done for us, right? So we're going to redraw that. What about our FPD? What should I expect on my FPD? Well, we literally did this setup right. I would be very shocked if anybody didn't have these right now. Very shocked. The same exact setup as the previous problem, but there is that change, right? L of X. Right, L of X. So let's talk inputs and outputs. What are my inputs and what are my outputs? Let's talk global inputs. What are my global inputs here? What's my global input? Ian. Okay. What's my global output? What is the overall effect of me putting Ian? X. Awesome. What about just circuit side? What do I have as my input to the circuit? Ian. What's my output from the circuit? What is my input to the electrical or the mechanical system? The electromagnetic force, right? Which is a function of I sub L. So really I sub L, or we'll take either one. What about my output from the mechanical system? X, right? So we see it. We can see how we chain these, right? So for inputs, right, these are my global inputs and outputs, right? And I wrote FEM. Well, FEM is just B times L times I sub L, right? The same thing as having I sub L. B and L are constant. Right? You can see how they change, right? Three ones are my global, where I got some input is the input that's started. And that's going to output the electromagnetic force, right? And then I've got my electromagnetic force in, and that's going to generate some position, right? In and out. So this is the part where it's going to get tricky. So let's talk about this. Right? Here are my truths, and I'll talk a little bit about this. Right? We know this one. We know Ohm's law. This was something that we gave last week in class. We talked about inductance, right? E sub L is equal to lambda dot. E sub L is equal to lambda dot. Right? And we know that what? That lambda is equal to L, I sub L, right? So if we take the derivative, right, we talked about this, right? And I'm going to claim that L sub x is equal to my initial inductance divided by 1 minus the distance that I've traveled divided by the total distance. So I'm claiming that the way that my inductance varies with position is this function. Right? I have some total inductance that I start with, and then I get some percentage of that as I move through my coil. Think about this, right? It's not, you're changing the inductance, right? In reality, you are changing the inductance based on how far, right? If this is my coil of wire here, based on how much of that magnetic field we are interacting, right? We interact with this magnetic field, we're moving that field and those wires towards each other, right? Another way of thinking about this, probably a better way of thinking about this is, if you had an electromagnet, right? You had a magnet, you wrapped a bunch of wire around it, right? And you started to move the magnet out of that wire, right? You're discharging part of the field, you're making the field smaller. That's what's happening here. As that metal plunger moves through the wire, you're changing the amount of field that you have. You're removing some of that interaction, right? And so it actually changes as a function of the position of the plunger inside of the coil of wire, right? And that seems problematic, right? Because we didn't model that before. We just did this straight up with a linear model. But well, we're going to keep going with this, right? So this is a little bit gross. How did you come up with that, Dr. Deagle? There's this thing, I don't know if you guys have heard of it. It's called Google. And you can type it into Google and like it gives you answers that you didn't even know that you wanted for things. Right? And also you should always believe everything that you read on the internet, right? That's the other 100%. Not really. All right, so what is L naught? L naught is described as mu times A times N squared. N is the number of coils that we have divided by the total length of wire. Right? A is our cross-sectional area, and mu is some constant. N is the number of coils, yeah. Because remember, the number of coils has some effect, right? If you were to slice those coils in half, you could look at the field line. The more coils we have, the larger, the more field that we get, right? Sorry, what was that? Mu is just a constant that's in there. I'm gonna be straight up with you guys. We're not gonna see this equation ever again. Okay, because this is highly nonlinear. This is a highly nonlinear system. What we are gonna do is later in the semester when we start talking about Simulink, we're gonna bring this model back though, and we're gonna test it and see how far off our linear model is compared to our nonlinear version, right? And to see, is it actually appropriate for us to simplify it down, right? That's what we're gonna see. All right, so here I am, right? I've got these things, and I can write my KVL as my truth as well, right? So KVL says what? Well, for this particular, we wrote this earlier. It's the same KVL. Right, we have this. Right, lambda here. Remember, I want to rewrite my lambda. Lambda is actually a function of x, right? Lambda is equal to Lx times I squared. All that. So if I want lambda dot, right, and this is what I was talking about, you need to do the derivative, right? Because lambda dot is equal to E sub L. It's written up here. I know that lambda is this, so if I take the derivative, lambda dot, right, that's just dl dt times I. plus L times di dt. Right? Because if L is not constant, then I have to take the first time derivative of the second plus the second time derivative. Right? That's what we have to do. Well, it gets better. It gets better. Because I only want this as a function of x, right? So I can rewrite dl dt using the chain rule, right? As dl of x, because we know L is a function of x, so let's take the derivative of it with respect to x, times dx dt, right? So just chain rule separate that. Plus L, yeah. And if you really wanted to, right, you could take this L of x that we wrote in the top right-hand corner there. You could take the derivative of that with respect to x. We're not going to do that today. We're just going to leave that as dl dx, and we'll use another variable to substitute for it, so we don't have to keep writing dl dx. Right? But be aware that that's where that comes from. Okay. All right, great. So that looks significantly grosser than what we had previously, right? That right there is not nice looking, and definitely it's going to definitely be non-linear. Okay. So what do we do? What do we do here? Well, we're gonna keep going. We're gonna keep going. I'm gonna put in another slide here because it'd be a good idea to do so. Oops. Okay. So we're going to leave that as our truths for our circuit, right? Those are the things that we need. We're not going to touch them right now. We'll come back to them during our reduction. Actually, you know what? Why don't we just do the reduction for the... No, all right. We're just going to do our mathematical truths for the other system, right? So here's our mechanical system. What do I have? Well, if you thought to yourself, it's going to be the same that we had before, then you're right, right? That's what we got. What's up? So the current isn't a function of x, right? The current is still just a function of time. The only thing that's changing with x is the inductance current, or the inductance constant, L, a capital L. So we'll see what happens in a second. It'll all come together, I promise. Because as it turns out, we're also going to have to rederive our electromagnetic force equation, because it's not constant. Okay? So we're going to talk about that right now, right? So normally, right, we have FEM is equal to B times L times I, right? Normally. But really what it is, it's the time derivative of zeta. What is zeta? Well, remember, zeta was what we're using for energy for the system. Right? Zeta is what we're using for the energy of the system. I'm sorry, that's not a function of x. That's not a function of t. That's d zeta dx. Right? And we wrote in class last week that zeta was equal to 1/2 L I squared. That was from Tuesday. Tuesday's class, it's on the slide, right? 1/2 LS. Okay. So if the electromagnetic force is just the derivative with respect to x of that, we know what? We know that I doesn't change as a function of x, right? So we can consider that to be constant with respect to x. 1/2 is a constant, but L is changing with x, right? So we can rewrite FEM is equal to 1/2 dl dx all squared. Well, hold up. What was dl dx? Isn't that just here? Yeah. And this is where we're going to introduce, which is just the x derivative of this guy up here, right? So do we have to take the derivative? And I said, no, we're not going to. We're going to now call that, we're now going to call that quantity L sub x. And we're going to roll with it.
Dr. D,
Yes.
are you writing on a different slide? I don't think that we can
Sorry.
see the next.
My bad. I had you on
Thank you.
that. My apologies. You guys will never know how I wrote those letters. You'll just always think that they just appeared. And if you go back and watch it later, it will also be frozen. It's a moment in time. It's all part of my nefarious plot. And you'll never see my handwriting. All right, anyway. Okay, so we're gonna call dl dx just L sub x. Why? Because it takes less time than writing dl dx. And also, I don't feel like doing that derivative. So I'm not gonna do it. If I really wanted to, right? If we really wanted to, we could, but it serves no purpose for us right now since this is a nonlinear system and we're just gonna leave it as a certain way. Right? Okay, cool. So this is FEM, right? This is FEM right here, this guy. That's what we're gonna use. And it comes from the energy, and the time, the change in the energy with respect to position. Okay. So what do we do now? We do the same thing, excuse me, that we've been doing. We're gonna do our reduction, right? And so we can do, we're gonna do our reduction, right? So if we start with the electrical model, right, what do we know? We know that lambda dot is equal to L sub x, x dot I, plus Li dot, and this is going to be equal to E sub L, right? That comes from that equation that we wrote before where we're just taking the derivative and then we split it up using chain, right? That's where that comes from. If we use KVL, which is the only equation we have in a single loop system, we get negative ER minus EL plus EN is equal to 0. I can substitute in some equations or some of my truths here. And I'll get this. Right? Remember, E sub L, this part, which is just this guy in the blue bracket, right? That's my new E sub L. We had to derive E sub L. That's pretty obvious to me that that's nonlinear. Okay. So now what do we do? Well, now we just group it in terms of our inputs and our outputs, right? So we'll have L sub x and I dot. I'm sorry, that's not L sub x. L sub x is a specific thing. That's L of X times I dot L. Draw I sub X. Plus R, I sub L, is equal to E in minus L sub X, X dot I sub L.
And then that line, the first one there is L times, like L of X, not L.
So this up here, the lambda, the llama right here.
No, in the most bottom, yeah, for both of them. For that one that you underlined in red, and then the one at the bottom of the page.
L sub X. This one here is L of X. So it's L as a function of X, not time. And so this is
Thank
L
you.
as a function of X. Okay. That's it. That's where we leave this. Notice something interesting here. Because we've included this nonlinear term, does that look like anything else that we've seen, specifically when we've been talking about motors? Is there a term in the motor that is a function of the velocity that we characterize? Back EMF. This is the translational version of back EMF, except that in this case, it's nonlinear. So it would make sense, right? If I'm moving this through a coil of wire, there should be generating some, I'm changing the field as I go, it should be generating some back EMF again.
So, this is kind of the definition of, so it's basically saying that the voltage drops in the circuit with our current are equal to the sum of the, so the difference of the voltage drop in the motor is that. So we've been able to sidestep a lot of the dynamics by just calculating the voltage in the motor as a function of the speed essentially. Except for example, instead of accelerating and talking about the force of the string.
Yes. Okay. So this guy, this is our electrical system equation. And we're just going to leave it. Could we, if we wanted to, go and plug in our L of X, which we have? Yeah, sure. Could we take the derivative of L of X and plug that into? Sure. I'm not going to do that. Okay.
I guess I don't see how this is affected now. Yeah, one EI is equal to the sum of current voltage drop, because we still have time derivatives and space derivatives. So we still have two PDEs.
Yeah. Yes. So for analytically solving it though, right, for PDEs is
One math is how much study analytics is better. What do we need?
that's something we're going to investigate when we actually do the analysis. Right, but Simulink will allow you to input nonlinear systems with check. So analytically speaking, right, if you were to do it by hand, right, this you could linearize it, you could do it by hand, right, and it'd be all right. I guess the point that we're going to make later is exactly your question. Like, what have we bought ourselves by including this term, right?
Oh, well, I agree with her, yes. It's just a definition. Because defining the motor in its own terms. Well, it's not really motor.
Yeah.
It's all in the string.
Yep. All right. Let's do the mechanical system. So it turns out our mechanical system is not going to be that much different. Right? We're going to sum our forces, and what we have We got FEM minus FP minus FK is equal to M X double dots. And then we'll rearrange, we'll include our truths, right? I've got MX double dot plus BX dot plus K. X is equal to, well, that's going to be equal to FEM. Well, we just found out that FEM is 1/2 LXI squared. LXI squared. Remembering that LX is DL, yeah, right? And that's it. That's I sub L. That's equation 2. Leave it. Move on. What order system is this, right? So I'll rewrite the other equation, right? So we can look at the complete model, right? Here's my electrical system equation. What order is this system? Cumulative, yes. Yeah. Yep, Sean, that's it. Third order. How do I know? Well, you see, when you have a second order system and it finds companionship with a first order system, that becomes a third order. Another way of thinking about this is, well, another thing that you'll see later in the semester with this is when you take the Laplace transform of both of these and combine them, you will end up with a third order polynomial that you'll have to solve. Okay. Time. Got a little time. Got a little time. You guys have any questions on this? Seems roundabout. Why show you this if it's not linear and we're not going to do it? Well, we are. Right? But we have to remember that the real world is highly nonlinear, right? And the things that we're doing in this class are simplified to be linear, right? And is that a problem, right? This ties in a little bit with the ethics paper, right? Is that a problem? Is it problematic that we are reducing these systems in complexity? I mean, it depends, right? It depends. How big of a difference is there? Are you talking about an application where 10% difference matters or it doesn't, right? You're driving 70 miles an hour in your car, you set your cruise control and there's a 10% difference there, right? You know, plus or minus 7 miles an hour. Is that big of a deal compared to something that's super small scale, like trying to control blood flow or medication flow in a pump, right? Whereas you lose 10%, your dosage is completely wrong. It all depends, right? It depends on your application. Danny.
I would say you sort your quantity by the energy. So, figure model that. And typically, those well, but don't you see less energy associated with a higher order energy? So,
Yeah, so I mean, what we'll see, right, then that feeds into like a Taylor series expansion linearization, right? We typically don't take past the second term. And that's actually something that breaks out in statistical analyses as well. So I don't know if you guys are going to be doing any of that for your senior projects, but if you have to do like a primary component analysis or hierarchical statistical analysis, that's typically what you'll see is, you know, you'll start off with a bunch of things that are grouped together, and then you'll have outliers, basically. Right? So, you guys have any questions on this one? Y'all, you guys at home have been pretty quiet today. Can you hear me? Or it's probably not great. Trying my best to not blow out everyone's eardrums in the room, but hoping you guys can at least hear me.
Yeah, it
This
sounds
may
good.
this may be a bit redundant, but how did 1/2 L sub I squared come to be
Oh,
in the mathematical truths?
Yes. This guy right here,
Yes.
Li squared, that comes from the energy storage of an inductor, right? It's very similar, you'll notice, to the energy storage of a spring. This is just how energy is stored in an inductor, right? It scales with the inductance and the current. Right? That should be in your notes from last week on Tuesday when we went over the elemental equations for electrical systems.
All right. Thank you.
Let's talk about something that's, again, cool is a relative term. It's interesting. And we can talk about electrostatic micro actuators, right? So like a MEMS technology, super small scale. So imagine, if you will, so let me ask the question. What is an electrostatic micro actuator? Sure, Danny.
And apply very small like force attraction, dark particles rather than
So yes, it is a small device that, because of its small scale, can take advantage of electrostatic forces as opposed to electromotive. Yes. Right. Essentially creates a small capacitance, right? It's MEMS. MEMS. We don't have room for coils and fancy electromagnetic induction, people, okay? Nobody's got room for that. We've got air gaps and, you know, electrostatic charge. That's the scale that we're looking at. So how does it work? Use electrostatic force. So if you've ever, you know, combed your hair in the morning and you live, you know, in Phoenix, and it's right about now, right? You know, the static, and then you put the comb next to the faucet, right? Where the water's coming out, it actually bends the water. You guys seen that, right? It's electrostatic force. There's a small charge there. It's not much. It doesn't do much, but on small scale, it's enough to affect change, right? Well, that was a great place for me to put that picture. Fantastic. Electrical force of repulsion or attraction between charged particles. That sounds an awful lot like chemistry, right? Charged particles. I apologize. I didn't mean to scare you. I did not mean to scare you. What are some typical applications of MEMS? Well, surgical micro grippers, optical micro shutters. Electronics technology is getting smaller and smaller all the time, right? There were some guys when I was working at Pickett's Arsenal who were very interested in determining MEMS using applications, right? So how do we determine whether ammunition is safe or armed using very small scale devices, right? Which is that's kind of scary, because some of these are small enough that you could shake them loose, right? And so it's a major safety concern too, right? All right, so let's look at this. This is a typical micro gripper, right? So what do we have? We've got one side that we call the closure arm, and the other side is the drive arm. Okay, so the side that's connected to ground is our closure arm. There's also a little circuit here, right? We've got a small circuit that we built. So what do we have? We got this this voltage input, right? This goes into my closure arm, and on the back side, the drive arm is connecting it. So what is this actually doing? This is changing the capacitance between these two devices, right? So energizing the voltage source produces an electrostatic force that pulls the drive arm to the closure arm, right? So we charge up the closure arm, it's going to attract the drive arm, right? When you turn it off, the spring and the damper bring it back in a nice and controlled way, right? work on a micro scale, right? So they're super, super. We'll do this one. Let's do this one. You guys take a couple minutes and do your diagram, and then we'll review. Don't worry about that. Your 45 minutes is up from before that we used. All right, you guys have diagrams, or you want another 2 minutes? I'm gonna assume if nobody at home says that they want 2 more minutes, then that somebody at home can show us their diagram. Yeah. I will pick at random. I will unfreeze the screen. Rowan, since you are being very helpful in managing the chat today, you may pick one person to show their diagram from the list of Zoom attendees, which are right here on the right-hand side of the screen. Except me, you can't pick me. It's a good strategy. I'm sorry, what was that? Cody? All right, Cody Wood. Would you please share with us your circuit diagram? Oh.
I don't have one.
All right. You have an FPD for the mechanical side?
No.
Oh, well, what you been doing the past couple minutes? All right. Let's go with Alex. You show me your circuit diagram, please. What is going on here? Alex, you have a circuit diagram? Because just because you're not here in the room, I still need you all to participate in classroom activities. Okay, this is not just do whatever you want time. If you're just gonna do whatever you want, please don't come because this is detracting from people who want to learn. All right. I'm sorry, I'm getting a little bit frustrated. Does anybody have a circuit diagram that they want to share with everybody?
I may have something.
All right, good. Thank you. Thank you, Julius. What you got?
It's just a repeat mostly from the original, from what was on the board. But I found that from mathematical truths, the ER would just be RIR, EC would be theta dots, and I just got the EN negative ER negative EC equals 0. I just started out, sorry.
Oh, that's fine. I just was wondering about the circuit diagram, right? So yes, you're right. It's exactly the same as the one that was already there, right? The circuit diagram in most cases is like a gimme amount of points. You just need to redraw what was there and highlight what your currents are, right? That's basically it. If you have any loops, draw your loops, right? Thank you. Does anybody have a free body diagram that they would like to share?
I have mine I can share, but I'm not really certain on the mechanical side if it's correct.
Oh, that's fine.
Just let me see if I can share it.
Sure. Thank you, James.
Yep. Is that showing for everyone?
Yeah, you guys can see that, right? Yeah, that's it, right? You've got an electrostatic force playing towards the circuit, right, to the left in the positive direction. Because of that, your spring and your damper are fighting that motion, right? Danny. Yes, in the same way that we thought about flux. Yes.
Could you repeat his question? We didn't hear.
Danny asked if this was, is it useful to talk about charge when we're doing this? And the answer is going to be yes when we get to our mathematical truths. In the same way that we use lambda in the previous one for L of X, right? Because in this case, the capacitance changes as a function of position, right? In this case, yeah, Trenton, Cameron got the answer to your question. But that's why, because we're moving to the left, so the spring and the damper are going to fight that. Right? All right, cool. Thank you guys.
Yep. But is mechanical side correct? I'm assuming.
Yes. Nailed it.
Okay. Just want to make sure about that part.
That was good. Good stuff. All right. So these are the diagrams, right? You know, the one thing that you could add here, right, just so you don't forget, is that we're going to have some KVL loop, right? It's a single loop circuit. So we have to basically, we're locked into using KVL for this, right? To figure out what it does. The trick here is going to be, how do we get our definition for, how do we get our mathematical truth for the current, right? How do we figure out what the current is? Because just like in the last one, we can't assume that C is constant, right? C changes as a function of that distance. But as we close the gap, we will presumably have more capacitance, right, as we close the gap. So how do we deal with that? All right, well, let's talk about this first. Right? Inputs. What's my input?
En
There it is. En. My output.
X.
There we go. All right. Those are the global ones, right? If we wanted to get down and dirty with it, right? You also have E sub C. Right? You've got En that's going to produce, remember, we have a capacitor there, right? So your output from the circuit is E sub C. E sub C is going to affect our electrostatic force in some way. We haven't talked about in class how we determine what electrostatic force is, right? We talked about electromagnetism. It's going to be a little bit different. And what we're going to do is we're going to derive it from our charge. Okay. Yep, that's what we're going to end up doing. Charge and the distance between the plates, right? So what about our truth?
Sorry, why is it E sub C?
What is my energy storage element that is in the circuit?
The capacitor.
Right, and when we have a capacitor, what do we use as a dynamic variable?
Oh, the E sub C.
Remember, when we have circuits, we're going to write everything for circuit analysis in terms of our input variable and either E sub C or I sub L, depending on what our energy storages are. You will need to do as many as we have actual storage elements.
Is that FES not a input?
FES is just a function of E sub C, right? In the same way that our electromagnetic force is a function of the current through the inductor, right? And so it's one or the other. If you wrote FES, you're not wrong. FES is a function of E sub C.
Okay.
In this case, that's I sub C. We know that I sub C, well, we can't write that yet. We know that Q is equal, Q dot is equal to I sub C, right? Well, let's back that up. Q is equal to C of X E sub C, and Q dot is equal to I sub C. So in the same way that we had it before, Q dot has to be equal to dC dt dC plus C dEC, right? C is not constant. Not constant. We can't just pull it out. We have to do the first times the derivative, the second plus the second times the derivative of the, and then we can simplify this a little bit more, right? And we'll end up getting, I'm going to call this C sub X. Right? I'm not going to do the whole song and dance like we did before. We're just going to talk about what it is as a final portion, right? So what is this? What is going on here, right? Well, remember, we had to do a chain rule to separate dC dt into dC dx and dx dt. X dot is dx dt, and we're saying that C sub x is dC dx, right? So this is going to replace dC dx, okay? Where does that come from? It comes from the chain rule. It's the same thing that we did before when we were talking about flux, except this time we're talking about charge, right? So we had to bring this back to the derivation variable, right? We know that current is the derivative of charge. We know that voltage across the inductor is the derivative of lambda, right? We had to use those definitions to come up with what these are. Zach. So it starts off as dC dt, right? But then we're going to use the chain rule to change this to dC dx times dx dt, right? And because of that, that's where that x that we're going to pick up. I'm going to have to get used to not touching the board, right? That's where we pick up this x dot. Where we pick up this x dot. Right. Once again, you could, if you wanted to, climb on to Google and find out that your capacitance is this as a function of x. And if you wanted to plug that in, but notice it's a function of the distance, the area, the emissivity, and eta. To be honest with you, I can count on one hand the number of times I've had to use this equation, because this many. 0. Yeah. So once again, I'm not, as Dr. Stagg said, I'm not being facetious when I say that I had to look this up on the Google machine. That's a direct quote from Dr. Stagg. I swear. Part of it is. Most of it. Let's call it a paraphrase. Okay. All right, anyway. So we could take the derivative of that. We're not going to. We're going to work with everything like this, because this is just equal to I sub C. Okay? That's going to come back for us later. That's going to come back for us later. What else do we have? I've got KVL, right? Well, the KVL is going to tell me that EN is equal to ER plus EC. Remember, I need everything in terms of EC. So when I use Ohm's law, I'm going to plug this in for I sub C, right? And it's going to give me a messy equation. It's going to give me a messy equation. Let's finish this up for the circuit before we move on to the mechanical system. Right? So what does KVL tell us? Well, then we'll have EN equal to EC plus ER. Okay, well, it's EC plus R and C, right? Well, now I can plug in my I sub C that we just came up with on the previous slide. And what do I get? Well, I'll get E sub C plus R times Cx x dot EC plus C of x E dot C is equal to E. N. All right, and then I can substitute some things around. Right, so RC of x E dot C plus E sub C is equal to En of T minus RC sub x dot. I call that number 1. Right, and looks a lot like our solenoid equation, right? A lot similar, looks similar. So we'll hold on to that. So the trick here was figuring out that you needed to derive I sub C, right? That's what we needed to do. That was the trick. Once we have that, we're good to go, right? So far, how do we deal with nonlinearities, right? So far, you take it down as far as you can, and then you just won't. At this point, because we're not doing analysis, we can just plug in our nonlinear terms and move it. When we get to analyzing things, if we notice that our equations are nonlinear, we are going to have to linearize them, which is typically applying a Taylor series approximation for around a small differential, or in very in like 2-dimensional cases, 1-dimensional cases, it's basically making a point slope equation for the nonlinear algebra. We'll talk about that in a couple of weeks when we get there. All right, so let's talk about the mechanical side truths, right? And we'll do those in green because reasons. Well, you guys thought we should have Newton's second law, our damping force, and our spring force. And yeah, but also remember, we have our electromagnetic force, right? And when you use the same method here, we're going to take the derivative of our energy with respect to the position. And that is going to get us FES. What is our energy? Well, 1/2, right? 1/2 CE squared C, right? So, all right. So d zeta dx. Yeah, let's start it this way. Zeta is equal to 1/2 C EC squared. So if I take the derivative of this with respect to x, I'll end up with 1/2 dc dx times EC squared. And this is going to be FES. So we'll rewrite this as 1/2 C sub x EC squared. And we use this guy. Right? That's what we're going to use. Okay. Again, very similar to what we did with the inductor, right? Very similar to what we did with the inductor. Very similar. You guys have any questions right now? We'll tie this problem up and then we'll be done, right? Because class is basically done anyway. Interesting.
It's something that's really only possible with the substitution, not the linearization.
It's not a linearization.
Oh, yeah, no, I thought it was
No. We're just, for right now, we're just saying, hey, look at this model. I realize it's nonlinear. We're going to shelve that until we get into linearization after the first exam. For those of you who didn't hear, Danny was asking whether this was a substitution or a linearization. It is just a substitution. We're just basically understanding that we're making a nonlinear equation, right? And we'll learn how to deal with that in a couple weeks.
For the fixed, so we can, I know it's not, we can now look at the fixed. I see why, if people use these variables now, because we fixed points in terms of those variables.
Yes. Okay, so let's tie this up, right? Some of the forces, what do we got? Well, we've got FBS minus FB minus FK is equal to MX double dot, right? Rearranging and substituting, I'll get MX double dot plus BX dot plus KX is equal to FES. Well, I know what FES is, right? So I can plug in all of my things and boom. Equation 2, right? Model complete. Great success. Again, right, we have a non-linear third order system. So how do we deal with that? So right now, the way that we deal with that is we're just going to leave it. We can deal with a nonlinear system through this part of the 5 steps. Through step 4, right, you can have a nonlinear model, and that is fine. Once we go to analysis, then we need to worry about whether it's linear or not. So for right now, it's just substituting things in and leaving it as is. Okay?
Doctor, do you have a question?
Yes.
So on the mechanical equation number 2, you have half CX or C sub X squared. Where'd that squared come from?
There shouldn't be one there. It's a typo. My
Okay.
typing is bad. I apologize.
No, thank you. I just was confused.
Sorry. It's poor typing. All right. We're done, guys. So
You get this around, fit that vehicle.
yeah, the beekeeper.
You really, no, you really get the Star Destroyer and
Thank you. That's it for today. I know it was another exciting lecture. Everybody, very excited. All right, for next class, if you guys are going to be here, please make sure that you bring your laptops, right? You still need to be on the Zoom meeting if you're in class, because there is still going to be breakout rooms for you to work with your groups. And you can't do that if you don't have your laptop and are on Zoom. So please make sure that you're doing that, because half of your group will be in class with you and half will not. So there's that. All right, cool. Got office hours from 3 to 5 today. Just give me a couple minutes because I'm teaching class until 3 right after this. So there's that.
This may be a bit redundant, but will homework 3 be on the quiz? Exam?
What's that, please?
This may be a bit redundant, but will homework 3 be on the exam?
Homework 3 is exam eligible. Yes, everything up to Tuesday of next week. Anything
Okay.
else from now until Tuesday is exam eligible.
Thank you.
Yeah, no problem. I don't want people to forget how to do the stuff, and then you're gonna get a question from it on the next test, and I wasn't prepared for it.